We are back. We're going to continue our conversation about Le Chatelier's principle. In the first part of the video, in part one, we talked about concentration. We are going to now hit on temperature and volume, and we'll talk about what a catalyst and an inhibitor does. So hopefully me writing on the front side of this page doesn't bother you too much, having those marks underneath there. All right, so taking a look at temperature, I alluded to it a little bit when we did the other example in concentration. Temperature is the kilojoule part that we're interested in. So really, you can look at temperature just like any other component of the reaction. If you increase the number of kilojoules, the system's going to try and decrease it, and it will shift away from it. If you decrease the number of kilojoules, the system's going to try and put it back, and it'll shift towards it. But the one thing we want to add is the idea of favoring the endothermic or the exothermic process. So that's the one thing that temperature needs to have in addition to the shifting. So we'll take a look at this reaction first. Energy is on the left side in this case. Energy is acting as a reactant. So the forward reaction is endo, right? Because energy is going in. The reverse reaction is exo in this case. That's not always going to be true. It depends on where the energy is. If the energy is on the other side, like I have it in this second example, now here the forward reaction is actually exo and the reverse reaction is endo. So you've got to think about where the energy is and how things are going to shift accordingly. Okay, so if I increase the temperature, what does the system want to do? The system wants to decrease the temperature. So to decrease the temperature, it needs to use up the kilojoules. The reaction will actually start absorbing energy. If I add energy to the system's going to absorb that energy and favor the endothermic process. It's going to use it up to make those endothermic products. Okay, so since the energy is on the left, the system wants to decrease the energy, so it's going to shift to the right. It's going to favor the endothermic reaction. So it's going to favor the forward reaction, and it's going to not favor the reverse reaction. Again, once you know where it's favoring, what direction the reaction shifts, it's easy enough to figure out what will happen to concentrations. So the concentration of water, because it's shifting away, will go down. The concentration of hydrogen and carbon monoxide will go up. So once you know, again, what direction the reaction is going to shift, the concentrations are easy to predict once you get the hang of this. All right, but if I increase the temperature, the system is going to favor the endothermic reaction. So an increase in temp is going to favor the endothermic reaction. Okay, which means if I decrease the temp, the reaction is going to favor the exothermic. So let's just see what happens. If I decrease the temperature, the system's going to try and put some kilojoules back. The kilojoules are on the left side. To create more kilojoules, the reaction is going to shift towards the loss. It's going to favor the exothermic reaction, which in this case is the reverse reaction. So it's going to favor the reverse reaction. It's going to shift to the left. And so what's going to happen? In order to make more kilojoules, I also have to make more water. So the water is going to go up. In order to make the stuff on the left, the stuff on the right has to go down. So H2 and CO are going to go down. Let's go to that second reaction that we were working on. Okay, so if I increase the temp, what's the system going to try and do? If I increase the temp, the system's going to try and make that temp go back down. So what's the initial response? To shift away from that energy. So the energy's on the right side. That means I'm going to shift to the left. So what's going to happen to the components on the left? They're going to go up. A and B will increase. What's going to happen to the components on the right? Just like the energy, they are going to go down. And if I were to decrease the temp goes down, system's going to try and build it back up. It's going to shift towards the energy now. So the energy's on the right, so it's going to shift to the right. It's going to favor the forward reaction. It's going to favor the exothermic reaction to try and put those kilojoules back, which means everything on the left will go down and everything on the right will go up. Okay, so you can treat temperature just like concentration, except you got to think about exo or endo, because a lot of times that's the focus that you'll have, that the question will have. All right, are we good with temperature, I hope? Moving on to volume. Okay, volume and pressure. So this is all about collisions. If I increase the volume, what happens to pressure? Inverse relationship, pressure goes down, which means collisions are smaller. If I increase the volume, molecules get spread out, they don't collide as often. The system's going to try and counteract that. The system wants to have the pressure back to where it was. Well, in order to counteract that decrease in volume, the system is going to shift to favor more particle collisions, which means it's going to favor more moles of particles overall. So when you're looking at pressure, you actually want to count how many moles of materials you have on each side. Now, we're going to ignore carbon because it's a solid. So I have a total of 1 mole on the left here. I have a total of 2 moles on the right. So that's going to help me decide which direction the reaction is going to shift. You want to count the number of moles. Okay, so count total moles of gas on each side. Because remember that volume is only going to impact gases. Liquids, solids, aqueous, volume and pressure aren't going to impact. So if I make the volume go up, what am I doing? I'm decreasing the pressure. So decreasing the pressure means I'm lowering the collisions. In order to put the system back in equilibrium, I want the number of collisions to go up. I want pressure to go up. So if I want pressure to go up, I'm going to favor more collisions. So I'm going to favor more moles. So in this case, what side has more moles? Well, the right side. So I'm going to shift towards the right. The reaction in the forward direction is going to go faster because that's going to increase the number of collisions that I have. So what's going to happen to O2, or H2O rather? It's going down. H2 and CO are going to be going up. Okay, but you're looking at the number of moles in order to decide. If I decrease the pressure, the system wants to build the pressure back up. I'm going to favor the side with more moles. If I decrease the volume, which means I'm increasing the pressure, the system's going to try and decrease the pressure. So it's going to favor fewer moles. So what side has fewer moles? The left side. So I'm going to shift to the left. More water is going to be made, and fewer carbon monoxides are going to be made. So I want to count the total number of moles on each side for pressure. So going to this second reaction that we had. So now let's take a look. Let me rewrite it down here. 2A, they're all gases. Okay, so now we don't have to keep pushing up and back and forth. So if I increase the volume, which means pressure is going to go down, system's going to try and put the pressure back up. So the system's going to shift to the side with more moles. So how many moles on this side? Because they're all gases, I got 3 here. I got 5 there. So if I want the pressure to go up, I'm going to shift to the side with more moles. So in this case, I'm going to shift to the right. So A and B are going down, C and D are going up. As a result, more particles are created, which means more collisions are going to happen. If I decrease the volume, which means pressure's going up, system's going to try and counteract by decreasing that pressure. So it's going to favor the side with fewer moles. Left side has fewer moles, so I'm going to shift to the left, favor the reverse reaction, favor the production of A and B. Going to decrease the quantities of C and D. Okay, so there's pressure. And then the last thing you have on your organizer is the idea of a catalyst. Okay, so let me get this so y'all can see it. So a catalyst is going to affect the rate of the forward and the reverse reaction equally. So a catalyst, again, you can't see it straight on. Catalyst isn't going to alter the position of equilibrium. It's just going to have both rates go faster. Okay, so both rates go faster, but equilibrium does not change. An inhibitor is usually something that removes a component from the reaction. So an inhibitor is going to do the same thing as decreasing the number of moles of materials in the reaction. Okay, so for example, if I added an inhibitor that pulled H2 out of the reaction, so something that's going to be eliminating H2 from the reaction, the system's going to try and put that back. So it'll shift towards that loss. So an inhibitor is going to behave just like removing a substance from the equation. All right, so I know that this is a complicated subject. I am actually going to look to see if there are some nice videos on YouTube so you can hear some other voices and maybe get a supplement to these ideas. Once you feel comfortable, you've got some problem sets to do in your binder. Thanks for listening.